Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 21 in the course Advanced Robotics. In the last class, we started our discussion on linear control systems, and we said that we understand that a robot manipulator is essentially a nonlinear system, because the equation of, when we studied dynamics, we saw that the equation of motion is a nonlinear coupled differential equation. But we make the assumption that this is a linear system, and we proceed with linear systems control theory. And today we'll proceed from where we left in the last class, where we talked about the position regulator problem. Today we'll look at partition control system, which can also be used to control nonlinear systems. Then we'll look at a little bit into stability, and then go into actual design of PD and PID controllers. Now, a couple of things to note, which I've reiterated quite a few times. The basic objective is, or the basic approach is, to model the complete robot manipulator control system as based on independent joint control. That means every joint is being controlled independently, although we understand that they are actually coupled. Okay, so these are some assumptions that we make. So please understand that robot control is when we are looking at control system design, we are making a lot of assumptions. Okay, so you should be very clear what are these assumptions and what effect do they have in the actual control system. Okay, so today we continue with our discussion on linear control systems, and we are looking at independent joint control systems. And what we essentially talked about in the last class, I'll go through it very quickly. So we essentially said that if you know the equation of dynamics, if you know the dynamic equation, which is tau is equal to m theta theta double dot plus v into theta theta dot plus c theta. Now if you know this, then one way would be that we can have a trajectory generator. Okay, so from my trajectory generator, for example, if I have a single link, let me look at it this way. This is two links, and I have a trajectory there that I want to follow, and I also have a trajectory at the joint levels, so theta 1, theta 2. I do have trajectories of this in terms of a cubic polynomial. So if I have my theta t is equal to a naught plus a1t plus a2t squared plus a3t cubed, which is a cubic polynomial. Now from here, by differentiation, I get theta dot t, and I get theta double dot t. So I have position, I have position, I have velocity, and I have acceleration. Now if I know the trajectory, and from the trajectory equation I can get position and velocity and acceleration, and if I give that as input to my dynamic equation, which is here, then I can compute the torques. Okay, so suppose you know the dynamic equation, which is given here. From the trajectory generator, you can get position, velocity, acceleration. Now if you give that as input to the dynamic equation, you can get the joint torques. So I get what is my tau 1, and I can get tau 2. Then I can give my tau 1 and tau 2 to the joints, and the robot will move. Now it seems like the system is going to work if you operate this way, but in actual it will not. Okay, so first of all, you see that this is an open loop system. Okay, so whatever we are computing in terms of position, velocity, and acceleration, we are giving to the dynamic equation. We're computing the torques. The torque is going as input to the joint, and the robot is moving. Okay, now why this will not work? Because there are a lot of assumptions when you're computing the mass matrix. For example, we said that the exact mass or the inertia matrix of the links, it would be extremely difficult, if not impossible, to compute. Why? Because there are gears, there are motors, there are encoders, there are wires, there are connectors. So you will not be able to get an exact inertia tensor, because of which there will be approximations, which means that the torque you're going to compute is going to be off by some amount. It will be approximate. Okay, so if it is approximate, obviously when you are applying that torque to the motor, what is going to happen is the final trajectory will be a little different. Okay, so please note that this looks like a good way of controlling a robot, but it's not possible to control a robot this way. Okay, now we also talked about the behavior of a system, and we said that if you have a spring mass damper system, so you have an MBK system. Okay, so you have mass, you have spring stiffness there, and you have damping here. So if you have a system of this nature, then I can write my equation of motion this way, plus kx is equal to 0. Okay, and it is going to behave in a particular way depending on b squared is greater than 4mk, or b squared is equal to 4mk, or b squared is less than 4mk. Okay, so depending on that, it is going to behave in a particular way, whether it is going to be overdamped, underdamped, or critically damped. And we normally choose this for our design. We choose the system to be critically damped. Okay, now in terms of now if you look at in terms of the, if I disturb the mass, take it to a position x, and this is my axis time, and if I leave it, then what is going to happen is it is going to behave in a particular way. So it will keep oscillating like this, or it will come like this, or the third response is that of critical damping, where it may oscillate a little bit and then it will come like that. So this is my critical damped position, and this is the kind of behavior that we want. Okay, so what we need to understand is that we always choose critical damping as the kind of behavior that we want. Now the first kind of simple controller that we talked about is a position regulator. Now the position regulator essentially keeps the position in a fixed place regardless of the disturbance forces. Okay, that is basically called a position regulator. This is not a trajectory tracker. Okay, so this simply attempts to maintain the position of the block in one fixed place regardless of disturbance forces applied on the block. Okay, so how do we go ahead with this design? We say that this is equal to f, because I'll need to put an f. So this f should be proportional to what? We said this f should be proportional to, this should be proportional to the distance, so it is equal to kp into x, and should be proportional to the velocity, so we say it is into x dot. Okay, so our position regulator controller is written in the form mx double dot plus bx dot plus kx is equal to minus kp into x minus kv into x dot. Okay, now I can bring this and this on this side, and what we basically get is mx double dot plus b plus kv into x dot plus k plus kp into x is equal to 0, and this is written in the form mx double dot plus b dashed x dot plus k dashed x is equal to 0. Okay, now for critical damping, we know that b dashed squared is equal to 4m k dash, okay, for critical damping condition, and we have to choose a value of kp. Okay, and then using that we can basically find what is the value of kv. Okay, so given choose or given numerical value of kp, we can find what is kv. This is something I did in the last class. Okay, now we said that the only issue here is that this is a position regulator, it is not a tracker. And also we looked at problems that can come in terms of inaccurate mass damping or stiffness estimations. Okay, so the other kind of controller that we look at is basically looking at what we call a control law partitioning, and we try and reduce the system to that of a unit mass. So how does this work? So basically we try and have a model based portion and we have a servo portion. Okay, so we try and divide the controller in two parts. We have a model based portion and we have a servo portion. Now what is this model based portion? Model based will contain the m, b and the k parameters, and the servo will contain the gains, so kp and kv. So in the previous case, if I go to the previous case, what we have seen is that in the control system you have a in the equation that I have written here, there is a kv and there is a kp. Okay, this is basically in terms of servo or the gains, and then there are the model parameters, which is the mass. So we have a mass, we have a damping, we have a stiffness k. These are the model parameters, which depends on the robot system itself. Okay, and kv and kp are the servo or the gains of the control system. So what we can do is we can try and divide this into two parts, having two sections. So how do we do that? We have mx double dot plus bx dot plus kx is equal to, let's say, f. Now in the previous case, minus kp into x and minus kv into x dot. Okay, now what we are going to do is we are going to say that this f is equal to alpha into f dash plus beta. Okay, so we are further breaking this f into two parts. Okay, and here m is equal to alpha, and let me say beta is equal to bx dot plus kx. Okay. Now, so if I put this back into this equation, what would happen is, what would you get when we put this back? So I have mx double dot plus bx dot plus kx is equal to alpha m into f dashed plus bx dot plus kx. Okay, this is what we get. So from here, what will happen is, if you look, this will cancel with this, and this will cancel with this. So what do we get? X double dot is equal to f dashed. Okay. This is called the control of partitioning. This is also called the control of a unit mass. Control of a unit mass system. So it is like there is a unit mass there. So we have reduced this to this. Okay. And what is the advantage of this? Let us have a look. So the advantage of this is that now I can control it in a much easier way. How do I control it? So for controlling it, what we do is x double dot is equal to f dashed, and f dashed I take it as minus kv into x dot minus kp into x. Okay, so from here, what do I get? I get x double dot plus kv into x dot plus kp into x is equal to 0. Okay, so this is my equation now, and it is like the mass is a unit mass there. Okay, so for critical damping, I'll be requiring b square is equal to 4 mk. So for critical damping, CD, let's say critical damping, kv is equal to 2 root kp. Okay, for critical damping case, and I have to choose the suitable value of kp and then find the value of kb. Okay, and then see whether we are satisfied with the response or not. So this is basically called control law partitioning, where we are dividing this into two parts. One is the servo part, and the other is the model part. In terms of control system diagram, what we are doing is we are writing it this way, or we are drawing it this way rather. So this is my model part. This is the model side, which contains the mass, which contains B, and which contains K. And this is my servo side, and this is partitioned. Why is it partitioned? Because you can see the servo is on this side and model is on this side. So model is this side and servo is on this side. So if there is any change on the model, it will be taken care of in this loop. If there is any change in the servo, it will be taken care of in this side, and they are completely partitioned. Okay. Now we'll see that this kind of partition control system is also useful in the case of nonlinear control systems. Okay. So if there is nonlinearity in the system, then this kind of partition control system can also take care of it. Okay. Now we will look at the trajectory tracking kind of controller. Okay, so we are having a trajectory tracking controller. So in the previous case also, this was basically dealing with x. So the variable here, when I wrote my equation, it was basically x. Okay, it is in terms of x. Now we will talk about in terms of a trajectory tracking controller. That means I'm giving you a trajectory and you have to track a trajectory now. Okay, it is not only going to a simple position x. In the previous case, when we talked about MBK system, what we said is that I am here and I want to go to this position x. I want to go from here to here. But it's not tracking a trajectory. What is trajectory tracking now? Trajectory tracking would possibly mean something like this. I'm giving you a trajectory. So this is a tooling system, and I'm giving you a trajectory like this. It has to track. Okay. So it basically has to track these points and go from one point to another point. So from here to here, it has to track this trajectory and then go. Okay. So for the corresponding joints also, there is going to be a trajectory which has to track with respect to time. So here I cannot operate on x space or theta space anymore, but I operate in the error space. Okay, so what is this error space? I am at this position. Let me call this, suppose I am here. I want to go to this position here. So if this is my theta, just for example, if this is my theta 1 and that's my theta 1 dash, then I generate an error theta 1 dash minus theta 1 and call it E. Okay, then I start operating in the error space. Okay, so I don't operate in theta space, but in error space now. So basically here what we do is, that we generate an error. So what is this error? So we generate an error between the desired and the actual positions. So error is equal to desired minus actual position. Okay, this is exactly what I talked about here. So this is my error, and we call this error, which is equal to E. Okay. Then what I'm going to do is I'm going to use the partition control system, and operate in the error space. So in the error space, if I write now, then f dashed is equal to x desired, acceleration desired, plus kv into e dot plus kp into e. Okay. Now if I have a in the partition control system, control for unit mass, if this is my f dash, we saw the unit mass system was like this, right? So this one, it comes in here. So x double dot becomes equal to x double dot d plus kv into e dot plus kp into e. And from here, what do we get? I take this fellow this side, so it becomes x double dot d minus x double dot plus kv into e dot plus kp into e is equal to 0. So this becomes equal to e double dot plus kv into e dot plus kp into e is equal to 0. Okay. Now this equation is written in the error space. Okay. So this e, which is the error space now. So this is my control system for a tracking trajectory tracking controller, which is written in error space. Okay. Now what does the control system diagram look like? So let's write it again. We have e double dot. So we have e double dot. We have e double dot plus kv into e dot plus kp is equal to 0. Kp into e is equal to 0, and e is equal to my x desired minus x. So it can be theta desired minus theta also. Okay, that is my e. So what is required? We have two loops here. Okay, so in the model part, what we are going to have is the model parameters m, b, and k that we have seen. Okay, because our original equation was mx double dot plus bx dot plus kx is equal to f, right? From there we have come. So my model parameters m, b, and k are on the model side. So this is my model side. Now in the servo side, we are in error space now. Okay, so if you are in error space, basically what we need to do is I need to get my e is equal to xd minus x in terms of, I need position, in terms of error, velocity, and acceleration. So this will become equal to x d dot minus x dot, and this will become equal to x double dot d minus x double dot. Okay, so how am I computing them? So I have my desired acceleration, desired velocity, and desired position, and this is my servo side. Okay, so you can see what is happening is that in this summing block, it is x dot x. This is what is happening, and then it's going forward. So e dot is equal to, you can see x dot is coming from this side. Okay, and my x d dot is coming from the left hand side. They are being computed, and we are getting e dot, and e dot is getting multiplied by kv, and is going forward like that. Okay, so this is how a trajectory following controller works in error space, and we operate in the error space. Okay, so because the objective of the manipulator is not only go from one point to another point, but it also has to track a particular trajectory when it is going from one point to another point. Okay, and in such cases we use the. Now point which I forgot here is, let us just go back here and look at this. Now suppose we are having a partition control system like this. Okay, and we have been saying for so long that we are talking about linear control systems. Okay, linear control systems. Okay, and I'm writing my equation as mx double dot plus bx dot plus kx is equal to 0. Now in this, is this linear? For example, this is friction, and friction, is not linear, it's non-linear. What about spring? Well, spring is linear only in a very small region. Okay, so if you look at a spring, let me look at a spring like this. One end is fixed, and I'm giving a force F. This is my del x. Then F is equal to K into del x. Okay, this is only for a very small region. Okay, outside that region, this doesn't hold anymore. So if I draw the graph of deflection versus force, okay, so this is my force, this is deflection, let's say del x. So the graph will not, it will be a straight line like this, and then it will go up like that. Okay, so initially it could be a straight line like this, and then that is linear, then it goes off like this. This means that after some time, after this much, it is linear only here. After that, it becomes like this. Okay, why? Because further deflection will not be possible. You can imagine that. Suppose I keep giving a force, it will compress. Once the coils get compressed, then you have to give a large amount of force to get deflection. And that is basically shown here now. Now this is nonlinear. So we can write the equation as F is equal to K into X cubed. Okay, that is one example. The second is friction here. Okay, friction is nonlinear again. So friction Bx dot can become equal to sigmoidal function into, okay, so that can become friction. Now this is again nonlinear. So in my nonlinear control system, I could have B sigmoidal function into plus K into X cubed. This is a nonlinear system. And this would still work here. Why would it work? Because we have divided the servo part and the model part separately. The model part here is taking care of all the nonlinear parts, whereas the servo part is taking care of the gains. So this type of a control system also works for nonlinear control systems. Okay. Now the other example before I proceed is we know that in the case of the dynamic equation, how is the dynamic equation written in the case of a real robot? Tau is equal to m into theta double dot plus v into theta dot plus c theta. Okay. So what I can do in the case of a real robot, when I know the system dynamic equation, then I can put v into theta dot here plus c into theta in this block, and my mass m theta can go there. Okay, so if you see that the equations are very similar, this equation is similar. So I can actually control robot manipulator for which I know the dynamic equation of motion this way by putting the model parameters here and putting the servo parameters there. Okay. So although this is a nonlinear control system, yes, but then we can control it this way because we are we are partitioning the two parts servo between. We are dividing the two parts into model part and servo part. Now let's proceed from here and look at trajectory following with disturbance rejection. Okay, so we are talking about disturbance rejection, or here when I say disturbance rejection, what does it actually mean, or what does dynamics actually do? Now we look at this serial arm manipulator. I have drawn it many times, and we said that velocities propagate from in this direction, theta dot propagates, and forces propagate in that direction. Okay, now because of this propagation of velocity and acceleration in the forward direction and forces in the backward direction, what happens is that each link affects the motion of the other link, which means this is a coupled system. Okay, and the equation of motion is given by tau is equal to m theta double dot plus v into theta dot, which is correlates the centrifugal forces plus the gravity term. Okay, so what is this fellow actually doing? Now this is the torque, the dynamic torque. This is the inertia. This is inertia. This is Coriolis plus centrifugal forces plus this is gravity. So what is these fellows doing? These fellows are disturbing the system. What does it mean? It basically means that if I'm trying to move the link in this direction, okay, you can imagine it is going counterclockwise. So counterclockwise rotation. What is the inertia fellow doing? It is trying to oppose the motion. Okay, and that is a disturbance. So what is the dynamics of the system doing? It is causing a disturbance on the controller now. So suppose I have independent joint control. I have a motor, encoder, and a gear sitting here. I'm controlling the motor to rotate the joint in that direction counterclockwise. Okay, but what is happening is because of this inertia, Coriolis, centrifugal, and gravity forces which are going in the other direction, they are tending to oppose the controller now, and that is basically a disturbance. So if you look at the previous figure that we talked about here, let me just rub this out. Now here, this is a trajectory following controller. On one side we have a model. Okay, this is my model, and this is my servo part. Okay, so basically what we are understanding is that we have partitioned it like this, and we have a model part and we have a servo part. Okay, but here we are still saying that we are completely ignoring the dynamics. So what is the dynamic fellow doing now? What is the dynamics doing? Now the dynamics is actually a disturbance force. So what it is doing is it is coming here now. Okay, so the dynamics is coming in from here and is causing disturbance on the system now. Okay, so if you're trying to go in some direction, is opposing that because of the inertia, Coriolis, and centrifugal and gravity forces. Okay, so this is actually a two input system. So far whatever control system we have been drawing is a single input, single output system. So what we call a CISO system. Okay, single input, single output. But this one is a multi-input, multi-output system. It has two inputs and it has two outputs. it has two inputs and it has one output. Okay, so in reality what we see is that what the dynamics is doing to the control system is that it is disturbing the control system, and this is my input here. So this is a two input system. This is my desired, this is my disturbance, and both of them are acting on the system now. Okay, so that brings us to the next question, that if that be the case, then how is it that linear control systems still function properly? We said that we are modeling this as a linear control system. Okay, that's the assumption. Second is independent joint control. Okay, neither of these two assumptions are correct. Okay, so it is not a linear control system, it's a non-linear control system. Okay, and then we are saying this is independent joint control. We are controlling each joint independent of the other one. Okay, and in reality we know it is not independent joint control because it is coupled joint control. Okay, but then the question comes, and then what is dynamics doing? The third thing is, what is dynamics doing? It is causing a disturbance to the system now. Now, in spite of that, why is it still working? Okay, why does the linear control system still work when all these things are there? So let us try to understand this very interesting question. Why does the independent joint control or PD control only with independent joint control, why does it work? Okay, we'll look at this in more detail as we go along, but initially just let's look at and try and understand why it works. Now, in the case of a robot, we looked at these three examples or the three cases. Number one is dynamics causing disturbance. Okay, so one was dynamics causing disturbance. Okay, number two was linear control assumption, although we know that it's a non-linear system. Okay, then the third thing we saw, non-linear. The third thing we saw was that, what was the third thing we saw? The third thing we saw was that independent joint control. Okay, so independent joint control. Now all these assumptions are actually, dynamics is ignored, but dynamics is there, which is causing disturbance. Linear control system, this is actually a non-linear system. And independent joint control, we are saying that this is actually not independent joint control. It's a completely coupled structure. Okay. Now for robot, there is even more difficult problem coming up. Why? It can pick up mass and leave mass. This doesn't happen in other control system, but in robotics this happens. That means the robot, let me look at it this way, the robot has an end effector, and in the end effector it can pick up a mass and it can leave the mass. So what does that mean? That basically means that this equation that you're writing, m theta, okay, theta double dot plus v into theta theta dot plus c theta, this fellow is actually changeable here. When it is picking up a mass, it is suddenly increasing by mg. Okay. When it is leaving the mass, it is suddenly decreasing by mg. Okay, so this is a variable mass now. Now you might say, so what? Now, so what means that if you look at this equation and think a little bit, let's look at that when we designed our position regulator controllers, it was mx double dot plus bx dot plus kx, or any kind of controller we designed. It was minus kp into x minus kv into x dot. When we designed the system, mx double dot plus p dash x dot, okay, when we designed it, basically it meant that this m, b and k are fixed. So when I'm doing my tuning, when I'm finding values of kv given kp, so kp is given plus critical damping, these two things are given, I find what is kv. Now when I find kv, the mass mbk is actually fixed. mb and k, you cannot change them, because if the m changes, what will happen, this the value of kp, the value of kv is going to change, the behavior of the system will change. Okay, I hope you understand what I'm trying to get at. That once you have designed your controller, if the mass starts changing, okay, then the tuning will go completely off. The behavior will change. Why? Because you have tuned it for a particular mass. You are using this critical damping b squared is equal to 4mk. Okay, and this fellow has changed now. Okay, and if this fellow changes, automatically the critical damping is gone. But in spite of that, the independent joint control still works. Okay, what is the reason? So in robotics, there is an additional problem. The problem is that the robot can pick up a mass and it can leave a mass. Okay, it picks up an object, puts the object somewhere. which means the mass has suddenly increased and then the mass suddenly goes down. So the tuning should actually go completely off. But in spite of all these four problems, the controller still works. Now, so the question being asked is, why does it still work? So let's look at this, try and understand why does it work, and then we'll look at more details of the actual control. So let's say this is my motor shaft, and the motor shaft is going out, and there is a gearbox which is sitting there, and the gearbox is connected to another gearbox. Okay. And this is my link which is rotating. Okay, that's not a very good figure. Yeah, so this is a gearbox there. There's a this is a, yeah, that's a gearbox. Okay, so let's say this is my motor on the left hand side. This is my motor. Okay, motor has inertia Im and produces a torque tau m, and theta m is the angle of rotation. Okay. And it has damping. Let's say there is a damping here which is Bm. Now on the link side, so this is the motor side. On the link side we have the link inertia, which is let's call it IL. So IL is the link inertia, and the motor angle is theta L, and there is some damping which is BL. Okay, and there's a torque on the motor side which is tau L. Okay. So when I'm giving voltage to the motor, what is happening? The motor is rotating. So I'm giving voltage input to the motor, plus minus. The motor rotates. Motor rotates means the rotor of the motor rotates. Okay, there is some friction which it has to overcome, which is Bm, and there is some inertia of the motor rotor, which is Im. Okay, now there is a gear ratio. Let's call this zeta. So zeta is my gear ratio. Okay, so what happens? The motor rotates, the speed decreases, the torque increases because of the gear ratio there, and then the link rotates. So this is the link side. Okay, now if I write the total, now we can see because of the gear ratio, let me say it as the gearbox. Okay, so there is a relation that tau L is equal to zeta times tau m. Okay, so the load side, the torque increases because there is a gear, and in terms of the motor velocity, which is equal to 1 by zeta into theta m dot. Okay, so these two things happen because there is a gearbox. The torque increases on the load side, and the speed decreases because there is a gearbox which is zeta, having gear ratio zeta, and zeta is greater than 1. Okay. Now if you write the torque balance equation, let's write the torque balance equation. That means from here I start writing the torque balance equation. So tau m, where is this torque going, or where it is getting consumed? It is rotating the rotor, theta m double dot, okay, plus Bm into theta m dot, plus 1 by zeta, there's a gearbox there, it is going that side, to I into theta double dot, IL theta double dot, plus B into theta L dot. So I'm assuming that K is equal to 0. Okay, so the equation is same as that, M x double dot plus Bx dot plus Kx is equal to 0. I'm saying this one is done, the stiffness is very small, so I'm saying K approximately is equal to 0, so K is ignored. Okay, now I have this equation here which relates theta L and theta M. So there are two variables in this equation. One is theta M and the other is theta L. Okay, so I can convert all the theta L's into theta M's. Okay, how do I do that? I can use this equation. I can use this equation and convert all the theta L's into theta M. Okay, so wherever there is a theta L, I will take it in. So what would I get? Tau M is equal to Im theta m double dot plus Bm into theta m dot plus 1 by zeta into, so theta L double dot would mean IL into theta m double dot by zeta plus B into theta L dot by zeta. Okay, so from here if I differentiate this again, I get theta L double dot is equal to 1 by zeta theta m double dot, right? So now I can bring the theta m's on the, so I combine all the theta m's. So what is going to happen is tau m is equal to Im plus IL into zeta squared into theta m double dot plus Bm plus Bl into zeta squared into theta m dot. Okay, so what we see is that this is my inertia part, this is my inertia part, and this is my damping part. Okay. Now something interesting to note here is that this zeta squared, let me mark it in red, zeta squared has come there. Okay, let me write the equation again because I need to do it here itself. So here, what is this indicating? This is indicating that IL, what is IL? IL is this one. So if I come back here, what is IL? This is my IL. This is the inertia of the, on the load side of the link inertia, right? So IL is my link inertias. And link inertia can change because of mg. Okay, so if link inertia is equal to 1, and just for example, if it picks up 5 kg, link inertia becomes equal to 1 plus 5, which is equal to 6. Okay, just for example. But when you're looking at the equation, what is happening is that this term here is the inertia term which is changing. It is equal to, so the inertia term here is equal to Im plus IL by zeta squared. So it basically means that even if IL changes, it is divided by zeta squared. So I'll say that again. If you go to this equation and see, this is my inertia. How is the inertia changing? When a robot picks up something, or a robot drops something, or puts it back, what would happen? There will be a change in inertia. There has to be, okay, because it's picking up a mass and then dropping a mass. But then what effect does that pick up and drop have on the inertia of that link? Okay, that is given by this equation. Now in this term, what we see is that IL zeta squared is coming here. Okay, so which means that whatever is the change in IL, it is divided by zeta squared. Okay, now if zeta is equal to, let's say 100, gear ratio is 100, then what will happen is, in this case, if it is changed by 5, then it is 5 by 100 squared. Okay, so it is 5 by 100 squared is the change. So it basically means it is 0.0005. That much change is happening, and this is almost negligible. Okay, this is extremely important, and I'll repeat it again. This basically means that when we write our torque balance like this, what we see is that the inertia of the motor, the rotor of the motor, which is here, plus the inertia of the link comes like this, and this is my inertia, the total inertia into acceleration. This is the inertia torque. Okay, now this total inertia which is coming, the inertia of the link can change, especially of the end effector. Why? Because the robot can pick up a mass, it can drop a mass. That means IL can change. But what we see is that IL is divided by zeta squared. So if there is any change on IL, but if the zeta is very high, then what is going to happen is that change of IL will not cause any effect because it's a very small change. Okay, so this essentially means that you must have, what is the moral of the story here? The moral of the story here is that you must have a gearbox. You must have a zeta and a high zeta value of zeta of the gearbox. First of all, you must have a gearbox. Please remember, if you're trying to control anything without a gearbox, you will not be able to control it. Why? Because, especially a robot. Why? Because if there is no gearbox, there is any change in the inertia, your tuning will go completely off. Okay? But because there is a gearbox, what is happening is that the change in the inertia is getting reduced by zeta squared, which is making the change a negligible change, because of which there is effectively no change on the controller. Okay, so pick up and drop an object, IL changes, but there is a zeta squared, and this zeta squared ensures that it does not have any effect on the controller. Okay, again we will see the dynamics doesn't have any effect on the controller. Similarly, we are saying this is a nonlinear control system. A PD controller can actually control it very easily. Okay, so although these are assumptions we have made which are not correct, but the robot control system using PD control still works. Okay, so please remember this, the moral of the story here is that you have a gear between the link and the motor and an independent joint control. Whenever I drew the system, whenever I drew many times, you'll remember I have a motor, I have a gear in front, I have an encoder at the back. So this gear in front is this gear which has this zeta, and without that you'll not be able to control the system. And the gear also ensures that whatever change in inertia is happening, that becomes negligible because it can be ignored. Okay, it becomes very small because of the gear ratio, which means you have to have a high gear ratio. Okay, that is the moral of the story. Now let's move on further to the actual design of PD and PID controllers. That means here, this was a very simple example where I drew a motor and I had a gear and I had a link side. Okay, now, and there was no controller here. In this equation, there is no controller. Okay, we did not put any controller here. This is just the equation of motion that I just looked at, the torque balance equation. Okay, now I have to add a controller here. Plus, I need to include the dynamic system dynamics now. That means when the other links are moving, what is happening to all the joints? That is something I need to include. Now, to include that, we will talk about how to design such controllers. Now, we also need to look at when we are when we design such controllers, we need to look at things like stability. Okay, so we will very quickly look at this. When we say a system is stable, a system is not stable. I had briefly talked about stability in the sense that when you have the characteristic equation, the roots of the characteristic equation should be on the left of the j omega axis. If it goes on the right, it becomes unstable. But I didn't say what is the stability and instability. Okay. So let's look a little bit very briefly. Now, as I said, that control system is actually a subject in itself. And I'm doing it just with a very briefly with respect to robotics. Similarly, control systems is a subject and stability is also a subject. Okay, and I'm just covering it very briefly in maybe 5 or 10 minutes only. So please don't think that this is all about stability and all about control system. It's not. This is not just scraping the surface. Okay, but just this much is enough for us to understand. If you take advanced level courses after this, more advanced level courses, then maybe it will be covered in more detail. Now, stable and asymptotically stable. These are two terms that we will look at. Now, before I go to that, the terms of stable and asymptotically stable, when we say stable, what do we mean? If we say something is stable, okay, what does it basically mean? Stable to what? Now, stable to a disturbance. Say, for example, I have a mass spring damper, mass spring and a damper. Okay, I give it a disturbance. What is the disturbance here? It's a force. So I give it a push. So I can give it a push or a pull, and I leave it. Okay. Now, if I ask you the question, is this system stable? What does it mean? It basically means that when I give a push or a pull, what will happen is the mass will get displaced. Okay, so maybe it will go this side. The mass has gone there. From here, it has gone here. Then I've left it. Now, when I've left it, it will tend to come back. Okay, and then it will come this side, and because of inertia, it will overshoot, go this side, then it will go that side, then it will go this side. So it will behave in a particular way. Okay, so if I draw the graph again, which I've drawn a few times, a couple of things to note. I have disturbed it, brought it till here. This time axis, I have left it. Now, it can either go like this, it can go like this, or it can keep oscillating like that. Okay, the question is this stable? Okay, then again, I'm coming back to two terms. One is stable, the other is a disturbance. Disturbance, you do understand that there is a force and it has been pushed. Now I'm leaving it, I'm seeing what it is doing. Okay, so a couple of questions here. It started from the original position x was equal to 0, and if I leave it, will it come back exactly to x is equal to 0? That's a question. Okay, start from x is equal to 0. Okay, will it come back exactly to x is equal to 0? That's a question I'm asking. Okay, so if I have my if I magnify this part a little bit, let me magnify this part. Okay, so I have disturbed it. Will it come like this and come like this, or will it exactly match? Or even if it takes one shot, sorry, that's not right. If it goes like this once, will it come here like this? Okay, will this come back exactly, or there'll be some error there? Please think about it. If I disturb the mass, and I leave it, okay, it will oscillate or it will move slowly, okay, something like that. So there are three possibilities: underdamped, overdamped, and critically damped. So underdamped, overdamped, and critically damped. These are three conditions based on b squared is equal to 4mk. But would it exactly come back to where it started? Would it come back to x is equal to 0? Now, what do you think? Okay, so stable is, if I'm disturbing it and I'm leaving it, it will oscillate maybe a little bit, but it will come back very near to where it started off. That's one. So stable is, it will come back to near 0 where it started. Let me draw it like this. This is the region. This is my system here. Okay, there is an outer boundary which is here. Okay, I disturb it. So I'm going to disturb this system here. So it will do something like that, like that, like that, and come back here. I hope you can imagine this is exactly this one I'm talking about. So suppose this is my mass there. I disturbed it. It went out of this small green region, roamed around somewhere in the red region, and then it came back. It came back somewhere near. So there's a very small region there where it came near there. Okay. So if this is my delta and that's my sigma, then this region is, it'll come back near to the origin where it started off. Then we say the system is stable. Now this behavior is similar to this one here. We are disturbing it and leaving it. It is oscillating a bit, but then it's coming back to near 0. Okay. Will it come exactly to 0? Probably not. Why? Because when you're giving a disturbance, what is this disturbance? Disturbance is energy. So some of the energy is getting consumed, some of the energy is getting stored. Now, in this particular case, in this equation, mx double dot plus bx dot plus kx is equal to 0. This is friction. This friction consumes energy. How does it consume energy? Friction consumes energy by converting the energy that you have given in terms of heat and in terms of plastic deformation on the surface. Okay, so friction is consuming energy, so you're losing energy. So if you're losing energy, it cannot come back to where it started because it doesn't have that energy. This fellow is basically going to absorb energy and give it back. There is no loss, no gain. A spring will just get compressed and it will expand, and then it will just give back the energy. So spring doesn't consume energy. It is the friction fellow which is going to consume your energy. Okay, consume, I mean that it will convert to some other form, or what I mean by energy loss. Okay, so friction causes energy loss. Spring doesn't cause, an ideal spring doesn't cause energy loss. Okay, so we understand what we mean by stable. Now, there is another term which is used, which is called asymptotically stable. So if I have a region here, the same thing. Okay, and if I have a larger region which is here. Okay, and now if I give it a push, suppose it goes around like this and it comes back exactly to the origin. It comes back to x is equal to 0 or origin. Then we say it is asymptotically stable. So this is stable, this is asymptotically stable. This is asymptotically stable. It comes back to the origin. Okay, so a system is stable, we understand. We also understand asymptotically stable. That means it comes back exactly to the origin where it started off from. Now there is another term which is called unstable now. Okay, so if I use the word if I say now unstable, then what is this unstable? So unstable is basically, now I'm drawing the same analogy. We have a small region in there and we have a larger region which is outside. This is my larger region which is outside. I give it a push, means I give it energy. It goes off like this, and goes off somewhere else now. Okay, this is a very small region sigma, that's the region delta. These are very, very small numbers. Okay, so if it goes off somewhere else, then we say this is unstable. Okay, so stable, asymptotically stable, and unstable. So in this particular case, if the system is unstable, then what is going to happen is your oscillations will start increasing with time. Okay, this is showing this behavior. Now for unstable system, to do this, you have to give energy. Right, if the spring mass system is going off towards infinity, now somebody is giving it energy from somewhere. Okay, only then it can do that. So this whole game of stable, unstable has to do with energy. Okay, so the moral of the story here now is, when we're talking about stability, asymptotic stability, unstable system, we are looking at energy that is being given in the form of a disturbance, which can be a push or a force or whatever, vibration, noise. These are all disturbance. That is energy. How this energy is being either consumed or lost or not lost. Okay. So if a system is losing energy, probably it will come back to the origin because it is losing energy, right? So this is basically what we are looking at is in terms of study of stable, unstable, and asymptotically stable systems. And the first person who looked at this was Alexander Lyapunov. Okay, he's the one who first looked at the concept of stability in terms of Lyapunov stability analysis. So Alexander Pian, long time ago, 1896. So that's almost more than 100 years ago. So he's the first person who looked at stability of a differential equation. Okay. Now our equation of motion can be expressed in this way: x dot is equal to a function of x. Okay. So basically, when we're talking about stability, mathematically, what Lyapunov looked at is determining the stability of a differential equation. So we are talking in terms of a spring mass damper system. And he also looked at, or he understood, that this business of stability has to do with energy. Okay, and what kind of energy? Energy loss. So if a system is losing energy, then probably it will come back to where it started. So this whole game is about energy. What kinds of energy? Kinetic energy and potential energy. So a system like a spring mass damper has kinetic energy, it has potential energy. So if a system is losing energy, then probably it will come back to where it started. Now, if it is not losing energy, then it will not come back to where it started. And if it is getting energy, then what is going to happen is it can go off somewhere else now. Okay, so this whole game has to do with energy and how energy is being lost. That is what Alexander Lyapunov proved. So this is called the Lyapunov's method, or Lyapunov stability analysis, sometimes called the second method of Lyapunov. Okay. So what we'll be looking at is, okay, so today we'll stop here and continue our discussion of stability in the next class. And something to keep in mind, some things which are very, very important, which we studied today. Okay, now it's very important also because it's not written in any textbook. Okay, that you need a gearbox basically to ensure that a controller actually works. So independent joint control works because there is a motor and there is a gear in front, and the gear must have a high gear ratio. Otherwise, what will happen is you'll not be able to control the system. Why? Because of all these problems that are there. Independent joint control, dynamics acting as a disturbance. A robot can pick up an object and drop an object, so the inertia changes abruptly. Okay? So, in spite of all that, independent joint control as a linear control system still works. Okay? Now, the second thing is the concept of stability, because when we talk of design of PD control and PID control, we have to look at whether the controller is stable. Now, we talked about mass spring damper system. Is this stable? So an MBK system, is it stable? Okay, how do you know? Okay, simply by saying that, okay, if I push it, it'll come back to the origin or somewhere near the origin. That doesn't prove anything. Okay, I have to mathematically prove that the system is stable. How do you do that? So we use the method of Lyapunov essentially to see what is happening to the energy. So if the system is losing energy, okay, then the system will come back to where it started off. Why? Because it is simply losing energy. Okay, and we have to prove it mathematically. Okay, and it's pretty simple how Lyapunov method of stability works. So we'll stop today and we'll continue in the next class. Thank you.